Hi, Anne-Marie. I hope this will help you as we go through your test. You missed number 1. A periodic wave is produced on a stretched string. Which one of the following properties is not related to the speed of the wave? And you answered tension in the string, but that isn't true. Remember in the simulation that we adjusted the tension and we would see that the waves appeared with different wavelengths, therefore they had different frequencies, and so we discovered that tension was related to the speed because both of those are factors in speed. The correct answer here is amplitude. How tall it is a factor of something else, not speed. You did well on 2 and 3, and on number 4 we have as the sound source approaches and then moves past a stationary observer, the observer will hear as it moves towards them a steady rise in pitch, but as it moves past you will hear a drop in pitch. So you only have half of the story here. This is both aspects of the Doppler effect. For this question, we are dealing with an open-closed pipe, just exactly like we did in our speed of sound lab. And I want you to think about what we did in the sway, where we looked at the harmonics. You chose that there are no harmonics, but we get a standing wave when we have 1/4 of a wavelength, and that is called our first harmonic. Now, for the string and the open tube, we had a second harmonic, but we don't get that in the open-closed tube because we have a node at the closed end and we have an antinode at the open end. So we skip the second harmonic, which would be right there because we can't end on a node, and we have another quarter wave for our standing wave in producing the third harmonic. So the correct answer for this would have been the odd harmonics are present. Number 14 was the next one you missed, and again, that's related to the speed of sound lab, where we used the tuning forks, where we knew the frequency, which we then converted to period. 1 divided by frequency equals period, and we had measured how long the tube was, and we multiplied that times 4 to give us a wavelength. So we would experimentally determine this as the ratio of wavelength to period, which is that graph that we kept going back to throughout this unit about the slope being the speed. For 15 through 18, you're given a scenario where the wavelength was shown in the picture to be 3 meters, which you correctly got. The next question asks, what is the period? Period is the time for one wave. And in the instruction, it says that the boat rises and falls 42 times in 60 seconds. So every time it rises and falls, that's one wave cycle. So the time would be in 60 seconds, that happens 42 times. And we want to know the time for one, so that would be 60 divided by 42, or 1.43 seconds. 17 asks for frequency. Frequency is the inverse of period, so that would be 42 over 60, the inverse of that, or 0.7 hertz. That's the unit. And number 18 asks for the speed, which is frequency times wavelength that we learned, or wavelength times the inverse of the period, whichever one you want to use, and that's going to give you a velocity of 2.1. This is 19, 20, and 21. And you correctly got that this was I'm sorry, it's so blurry that it's difficult to see on this, but this was your 580 hertz that was given. And this was also given 343 meters per second, and that was given in the instructions up at the top. What is the wavelength of the sound? To find wavelength, we know that velocity is equal to frequency times wavelength. So we are asking you to find the wavelength, and that would be velocity divided by frequency. For 22 through 24, you have two waves that are traveling in the same material but in opposite directions. And they're going to undergo superpositioning. And the concept there is that the amplitudes are additive here. So we take a look at the second picture and we see that the dark green wave has this point reaching A. At the same time, the light green wave has this point reaching point A. So the first question asks you to find what is the total amplitude here at point A. And so we have each box being 10 centimeters, so that would be a unit of 10, and the light green would be 20 total. They're both in the up direction, which we take as positive, so that would be 20 plus 10, or 30. Number 23 asks for you to do the same thing at C. That the light green one is at the resting point, the equilibrium point, and the dark green one is 10 or 20 centimeters above. So the additive 0 plus 20 would be 20 there. And the last question was for point E. Here we have 10 up, but 20 down. Negative 20 plus positive 10 gives us a negative 10 displacement or total amplitude. 25 through 31 deal with standing waves in a string. And so you can see from the sway and the activity we did with the beads on a string during class in the simulation, produce the first, second, and third harmonics with a half of a wave. So you can see that we have 1/2 wave when we have nodes where the string is affixed. And this is like a piano string or a ukulele string. It is fixed on both sides, and we set up the standing wave. You might remember the video of the phone inside the sound box of a guitar showing the creation of these standing waves, and that we have this kind of behavior in the standing wave. That's our first harmonic at the top, and our second where we have 2 half waves. The top one has only a half a wave connected node to node. So if we go to this question, number 25, the correct number of nodes you would see in the first harmonic would be 2 nodes, because that's our half wave in the standing wave. Number 26, you got right that the wavelength would be in meters. How many meters? It would be 0.47 meters given up there. And then number 27 asks for the number of waves in the second harmonic. So we have the half of a wave and the other half of the wave. So that gives us 1 whole wave, and the unit, the frequency, therefore, would be the velocity is equal to wavelength times frequency. So our velocity divided by our wavelength would be, it says 300 for this problem, 300 meters per second, and that our wavelength for this would be 0.47. And that would give us our velocity. Number 29 goes to our third one, and there we have a half a wave, another half a wave, and a third half of a wave. So we have 3 halves, or 1.5 waves here, and so the number of nodes would be 1, 2, 3, 4 nodes. Our wavelength here, since we have a total distance of 0.43 meters, and every time we have that length, we have 3 halves of a wave. So this would be the length of 1 wave, or the inverse of that, 2/3 of a wave in 4.73 meters, and that would give us our wavelength for that. And then number 31 is asking for the harmonic, and this would be the first, the second, and therefore this one would be the third harmonic. For this series of questions, 32 through 37, you have open tubes, and they're very much like the strings in that you have a half a wavelength standing wave created with resonance but instead of ending at a node where they're attached to the instrument, the open tubes have an antinode because they're open to a flexible boundary to the environment. So we again have a half a wave represented in the first harmonic. And so if I have a half a wave in a length that's 44 centimeters, to get a whole wave, I'd have to double the length of the pipe, or 0.88, 2 times 0.44, the length shown. In order for 33 to find frequency, we're again going to use the relationship that velocity is equal to frequency times wavelength, and we're solving for frequency this time because we knew our wavelength. For 34, we're asking for the number of nodes. So this time in the second, this is our fundamental, or our first harmonic. In our second, we again have to end at an antinode, and so we're going to have a half a wave, but I didn't get to the end, so I need to add another half a wave. Oh, I've got a whole wave here. I've got crest, trough, crest. So I have one wave, and my wavelength is 0.44 because it fits inside the tube, so my frequency would be 343 over my wavelength, using that equation again, over, my wavelength was 0.44, and that would be my second harmonic for number 35. 36 and 37 are about my third harmonic here, and I'm going to have a half a wave, another half a wave, and a third half of a wave. So this time I get 3 half waves, and so that would be 2/3 of 0.44 to get my wavelength, and my frequency therefore would be 343, this velocity, divided by whatever 2/3 divided by 3 is, sorry, didn't have my calculator, 2.293, and that would give me number 37, the frequency. For the final question, final 3 was exactly from your lab that we did, and I'm sorry the questions got cut off, but 42 asked for what data do you need, and again, what did you measure in class? You went out there and you looked at the tuning fork to get frequency, and then we measured how long the tube is, tube length. So that's what we were looking for. That was 42. 43 asked for you to say that you're going to change frequency is equal to the inverse of frequency is equal to period, and you wanted to multiply tube length times 4, because you have a quarter wave, to get 4 wavelength. Why did you want that? Because number 44 says how to find the speed of sound. 44, how do you get velocity? You get that from the relationship that it's the slope of a graph that has wavelength versus period, and we did these twice in class. So you would have the slope, which would be wavelength divided by period, so that you could find out the speed. I hope this helps you when you look back at your test. If you are not able to see what your answers are, do let me know, and I will go make sure that's turned on. I can also share with you your answer sheet. It provides your answers that you answered, but I don't want to print it because I think it's 14 pages long. So I thought if you need that as a PDF, I'll certainly include that. Hope this helps. If you have any questions, please let me know. Keep up your work. I appreciate your efforts and that you're curious and want to improve, and I'm here to help if any way I can.